For this example, we will first draw our free body diagram given here. Then we will apply our forces to our free body diagram, which is our weight at G. Then we have our normal force at the rear, our normal force at the front. Then we have our friction force at the front wheel, and our friction force at the rear wheel. Secondly, we will draw our coordinate system, I and J. And then our third step will be putting all the forces in vector form. So W will equal negative WJ. The normal force in the rear will equal NRJ. The normal force in the front will equal NF in the J. And then our friction force in the rear will equal negative FR in the I direction. And our friction force in the front, which will equal negative F I. And then we will put all of the acceleration in vector form, which is step 4. So A will equal AI plus 0J. And I'll pass this on to Zach.
So for step 5, we have to do Newton's second law. So the sum of the forces in the x is equal to mass times acceleration in the x. And for this, we'll get negative F of R minus F of F, the two front frictions, equals mass times acceleration in the x, and we'll call this equation 1. And then we also have to do sum of the forces in the y is equal to 0, and then we will get the NR plus NF minus mg equals 0. We'll call this equation 2. In step 6, we can apply Euler's equation. So that's sum of the moments about point G equals Ig times alpha. Set that equal to 0. So then with this, we'll get the normal of the front times the distance BF minus the rear normal times the distance BR minus force of friction times the distance D minus the force of friction in the rear times D equal to 0. And we'll call this equation 3. From this equation, we can get that the force of the rear tire, or the friction of the rear tire, is equal to mu sub k times the normal of the rear tire. We'll call this equation 4. And we can also get that the force of friction of the front tire is equal to the coefficient of friction times the normal of the front tire. We'll call this equation 5. So from this, we can get that normal of the front times BF minus normal of the rear times BR minus mu sub k n FD minus mu sub k n RD is equal to 0. and NR is equal to mg minus nf. Doing some further substitution, we can get NFBF minus mg minus nf times br minus mu sub k nfd minus mu sub k mg minus nf times d equal to 0. And if we expand this out, we'll get NFBF minus mg br minus NF br minus mu sub k nf times distance minus mu sub k mg times d plus mu sub k nf times d, still equal to 0. And from this we can solve the equation for the normal in the front, and that's equal to mg times br plus mu sub k times d, that whole term divided by bf plus br minus mu sub k d plus mu sub k d, and that simplifies to mg br plus mu sub k d divided by bf plus br. Now we can solve for the rear normal, and we'll get mg minus nf, which is equal to mg minus this whole term up here, which is mg br plus mu sub k d divided by bf plus br. So since the rear normal is greater than the front normal, the nose of the car dips downwards when the car is braking.